false? The invertible matrix theorem applies to all matrices. False. What kind of matrices did it apply to? False. Only square matrices. Just false is fine. Yeah. Right. If A is an n by n matrix, so it is square, which means the invertible matrix theorem does apply. If it has n pivot positions, then A is invertible. It's true. And if A is an n by n invertible matrix, so we know it's square, we know it's invertible, can you conclude that the columns of A span Rn? Yes, that's one of the many things in the invertible matrix theorem that's equivalent to A being invertible. Okay, so brief discussion of the reading. We're going to talk about the invertible matrix theorem today. This really pulls together many of the concepts from chapter 1 in one really important theorem, the invertible matrix theorem. But it only applies when you have a square matrix, which means n linear equations with n unknowns. So the invertible matrix theorem says that if A is a square n by n matrix, then all of these statements are either true or all of them are false. So if you're asked about anything, right, if you're asked about whether A transpose is an invertible matrix, if you can say yes to any of these, then you can say yes to A transpose is an invertible matrix, right? So if you're asked a question about any of these, you can figure out an easier one to answer, and it would be equivalent to the one that was asked, if that makes sense. Okay. So A is invertible means that A can be row reduced into the identity matrix. We talked about that last class. That's what it means to be invertible. And means A has n pivot positions. If it can be row reduced into the identity, it's got to have a pivot all along the diagonal. There would be n of those. And if it's a square matrix and it has n pivot positions, that means there has to be one in every row and one in every column. And having pivot positions in every row and every column tells us that AX equals B has exactly one solution. This one I wrote a little differently than the text did. So your text said at least one solution. And it actually is exactly, and they sort of bury it in a paragraph after the theorem, but it's really a key result. I don't know why they wrote it like that. But it has exactly one solution for every B. So because it has a solution for every B, that tells you that the columns of A span Rn, and that the matrix transformation X goes to AX is onto. And because there's exactly one, right, not just a solution exists, but it's unique, that tells you that the matrix transformation is 1-to-1, and that the columns are linearly independent. So like all of these are just all the equivalent ways of saying the same thing that we've been learning for the past, I don't know, month or so. All right, so, but remember that this only applies to square matrices. There are proofs in the text, but hopefully all of these statements are like, oh yeah, we already realized at some previous point in the semester that these things are all equivalent to each other. So remember that every linear transformation can be written as a matrix transformation, and the matrix of a linear transformation is called its standard matrix. So if T is a linear transformation from Rn to Rn, and it's got standard matrix A, T is invertible if and only if A is invertible, and it's T inverse's standard matrix is A inverse, just as you'd expect. So multiplication by A takes a vector X, you multiply by A and you get some new vector AX. If you multiply by A inverse, it just sends you back to where you started, X. All right, so do a couple of examples where we use the invertible matrix theorem. So I've got 4 matrices here. 2 of them can be seen to be singular just by looking at them. You can tell that they don't have an inverse. 1 can be seen to be invertible, that it does have an inverse just by looking at it. And then the fourth is not so easily determined, and we'll have to figure out another way. So which two of these matrices can you tell are not invertible? B and C, how come? Because of the row of zeros and the column of zeros, there's no way you can have a pivot in this row or a pivot in this column, right? So B and C don't have a pivot in every row. Don't have, we'll just say n pivots. Okay, so they are singular. If you don't meet one of those, if one of those statements from the invertible matrix theorem is false, then all of them are false. So these don't have n pivots, which means they are not invertible. Okay, so which matrix can be seen to be invertible just by looking at it? A, how come? No, you're right. Yeah, so if A transpose is invertible, then A is invertible. So if I write A transpose, right, then I have 3, 0, 0. So you just make the rows columns. -3, -4, 0, and 8, 5, -3. There's a pivot in every column. You've got 3 pivots. So 3 pivots for A transpose means that A transpose is invertible, which means that A is invertible. So that makes sense? It's not quite as quick as the other two, but you can still tell without having to do any row reducing. And then D is the only one left. You can't tell by inspection, I don't think, whether it is invertible or not. So what do? You got it. Row reduce it. If it turns into the identity, then it's invertible. And if it doesn't, it's not. So let's do that on the calculator. Okay, so I'm going to edit 3 by 3. So I have 1, -3, -6, 0, 4, 3. Oops. Oh, yeah. 0, 4, 3, and -3, 6, 0. You're done. It's invertible. Thank you. So matrix math, RREF. And it turns into the identity. Okay, so it row reduces to the identity, which tells me that it is invertible. Okay, next question. Leaving this one behind. Totally new question. If A is an n by n matrix, square matrix, and the transformation T of x equals AX is 1-to-1, what else can you say about that transformation? It's onto. Right, from the invertible matrix theorem. Because A is square, if it's 1-to-1, then everything else in that invertible matrix theorem is true. So T is also onto. And what else can you say about T? It's invertible, yeah. Because if AX is 1-to-1, that means A is invertible, which means that the transformation is invertible. I'll just write that out. A is invertible. About the, it says a bunch of things about A, not necessarily about the transformation. Yeah, we can say a whole bunch of things about A. We could say the columns. Yeah. Yeah, you can only be, if you have a square matrix, it's either neither or both. Yeah. All right, so we want to prove that if A is an invertible matrix, then A transpose must also be invertible. So this is part of the theorem. So you could just say true by the invertible matrix theorem, but I want to prove it, right? So that we're all convinced that at least this one small piece of the invertible matrix theorem is true. The rest of them we have proved in bits and pieces throughout the semester, but we haven't talked a lot about A transpose. So A is invertible, right? A invertible. That means A inverse exists, right? And A times A inverse is the identity, and A inverse times A is the identity. Okay, so A transpose, we want to prove that that's invertible. So that means I need to show something's invertible, I have to show that A transpose times something, we'll call it some other matrix C, have to give me what? The identity. I have to show that there exists some matrix that when you multiply it by A transpose, you get the identity. That's what it means to have an inverse. Yes? That's a great proof. That's a great proof, and it's way better than the one I was going to do. So let's do that. A invertible implies that A is equivalent to the identity matrix. And the identity matrix, transpose, is still the identity matrix. Right? So you can, so we should be able to start from A transpose and get the identity transpose, I think. So that's good. What if I wanted to do it this other way, though? I want to find a matrix C that when I multiply by A transpose, I get the identity. Any candidates for what that matrix C could be? It's going to be related to A somehow. Yeah. We have two matrices that we know exist, A and A inverse. One over A. A inverse. A transpose times A inverse would give you the identity? I don't think so, because A times A inverse gives you the identity. The inverse of A transpose, yeah. C is, this is what we're looking for, right? Is that the same thing as A inverse transpose? If you use A inverse transpose, it'll work. So A transpose times A inverse transpose should give us the identity. No, oh no, I'm not done yet. No. We have to show that this gives the identity. This is like my candidate for the inverse. Okay. if I can show that that gives the identity, then that definitely is the inverse of A transpose. So last class, one of the results from last class was that A inverse transpose is the same thing as A transpose inverse. Well, that's not good. I can't remember how I did this. Let's turn off the video.